Well, good afternoon. This is already 12:28. Sorry I'm late getting started, but we went long in my last class. It was a long line in the cafeteria, and then I just finished eating, so sorry I'm running late today. Well, I didn't just finish eating when nobody was up here. I went down and took care of a couple of other things, and also looked for your test, and I can't remember if I gave you the test last time or not, and that's where I got sort of confused. But anyway, nobody else is in the room, so it's supposed to be Cal 3, so I'm going to go and get started where we are. Let me remind you of this. First, please, folks, please do your student course evaluations. Please get those done. The dean is really on us pretty hard to get these things, our percentages up on the student course evaluation, so please do these. Number two, if I haven't already given you a test, I'm going to give it to you today. I'm hoping someone shows up to let me know that. We are going to finish chapter 14 forthwith, as in right now. I wish we had time to do 14.7. That is pretty important stuff. In fact, I may go over a little bit. Because that is on the test, but I won't count it if we don't get to cover it. So we'll try to cover that if we can, and then maybe get into a little bit of 15. Okay? You recall, I've got two of the three of you have turned in your paper, research paper. Only one of the three has turned in the first test. And then I'm giving you the second test today. So please, folks, get these things caught up. We will have classes normal today. That goes until, 1:55? Yeah. And then tomorrow, and then my office hours today are from 3:15 to 5:15. Tomorrow, my office hours are 1:15 to 3:15. Friday, I'm on the Birmingham campus, 7:45 to 11:45. All that is just normal. Next week, though, not quite so normal because it's final exam week for the most part, okay? I have a second mini-term class. We have one class on Tuesday and then the final on Thursday. So it's kind of like it's a class and a finals week for the mini-terms, but it's a finals week for the full term. So how things are looking for next week. Monday from 8 to 9:50, I will be in this room, 255, giving a review session for my Math 100 class. So that will be happening next Monday, 8 to 9:50. Okay? After 9:50, or say 10 o'clock on Monday, I'll be mostly in my office the rest of the day. Now, when I say mostly, that Math 100 class, they can come in and take their exam anytime they want to. And so that's pretty much it. So some of them may want to do their exam Monday morning, Monday afternoon, early evening, whenever I will be. And if I am giving an exam, what I do, rather than come back to this classroom, I go to the closest empty classroom to my office, okay? So that may be 263, it could be even 256, 261, 259, possibly even 254. Now, if all those are tied up, it could be next door at 257, or it could be here. So what my rule of thumb is, look for me first in my office. If you don't know that I'm in a class or in an exam or something, look first in my office, and then look in every room between 265, that's my office, and 255, that's this classroom. I'll probably be in one of those rooms. Now, for none of those, that may be I'm in the restroom, I may be at lunch, I may be something like that. So just wait a few minutes. I'll be back in one of those rooms or my office after that. So that's Monday from basically 10 till 5:15, probably in my office unless I'm giving an exam, and then I could be in any room between 265 and 255. All right, Tuesday morning at 8, I have an exam. It'll be here in this room, 255, from 8 o'clock until 9:50. Okay, exams are an hour and 50 minutes, almost 2 hours, not an hour and 15 minutes. So I will be in this room from 8 to 9:50. Pretty sure they'll take the full length of time, but if not, I'll maybe back in the office a little early. Okay? Then after 9:50, or say 10 o'clock, from then until 3:15, mostly in my office, but maybe in any classroom, giving a makeup test in between 265 and 255, anywhere in there. All right, at 3:15, I do have my mini-term class. It's not the exam, it's the class. So I'll be here in the classroom from 3:15, and I don't know how long. The class technically goes until 7:45. However, that's the last day of class. I have a feeling we'll finish early. We are in the last chapter now. We've got a 2-hour lecture on either a 2 or 4-hour lecture on Thursday, tomorrow. We'll mostly finish the chapter in that time. They have a test tomorrow evening, and then we'll definitely finish the chapter on the following Tuesday with probably plenty of time to spare. So once we finish the chapter, we'll have the last lab, and then I've given them the option they can either take their last test and the final anytime after we finish that last lab on Tuesday. They may opt to do it Tuesday afternoon, they may wait till Wednesday, or they may wait till Thursday, okay? I'm giving them the option because a lot of those students are from out of state or way out of town. You know, they're automotive students, they commute here, co-op here, and this is their last test, and they don't want to sit around for 4 days waiting on the test, so I've given them the option of taking the final early if they want to. Okay, so that's Tuesday of next week. Wednesday, I have nothing scheduled, but I'll probably be giving exams either in the Math 100 or in the physical science class anytime during the day. So mostly I'll be in my office, 265, but I may be in any room between 265 and 255. Then on Thursday, same thing, in the morning up until 3:15, from 7:45 until 3:15. I should be in the office most of the time unless I'm giving a makeup test, and then I'll be in any room between 265 and 255. Thursday afternoon at 3:15 is technically when the physical science exam is. And some students may opt to wait and take it then. If so, I'll be up here in the classroom and give the exam. It is not a long test. I imagine just about everybody will be through within 45 minutes or so. So I would say 3:15 to 4 o'clock would be the most I'll be up in the room. 2:55, after that I'll be back in my office or any room in between. Then the following Friday, that's Friday of finals week, I'll be back on Birmingham campus, 7:45 to 11:45, and then the following Monday is when, usually when grades are due. Now, last term they gave us an extra day because they had some problems with the system. They may give us an extra day this time too, I don't know. So anyway, if grades are due by noon on that Monday after finals week, I really need everything in next week. Absolutely. I don't have time to be grading and getting averages done and putting grades out there in just half a day. So please get everything to me next week. All right, so now here's another thing. I think most of you have been here long enough, you realize they shut down Student Suite during finals week. Now here's the reason for that. Our archaic old system that we have only has something like 16 or I think at most 32 portals. You know, in other words, that's the maximum people that can be on the system at any one time. Okay? Now, and this happened the first time we went to this system, during finals week, all the students were checking their grades almost constantly if they could get on. And they couldn't sometimes, But what that meant is none of the instructors could get on because all the portals were being taken up by students trying to check on the grades. Now, of course, we couldn't put the grades on because all the student portals were taken up. So the students didn't have the grades and they kept checking and we couldn't get on. Finally, they decided to shut down Student Suite during the week of finals. That's the only way we could get to put our grades on. So that's what they typically do, but here's what. I think most other instructors too, always put the grades first on Blackboard. That's where we do our averaging and all that kind of stuff. So the grades are going to be on Blackboard first, and then they'll go on the suite. You can access Blackboard anytime, finals week, whatever. So during finals week, don't check your grades on Student Suite, check them on Blackboard, okay? And whatever is going there, that will show up later on Student Suite. Okay, so that's what you do during finals week, and that goes up until whenever the grades are due, Monday at noon or Tuesday at noon or whatever they set as the deadline for the grades. Student Suite will be closed until then. All right, so I hope that's about all. One other thing. Please vote next Tuesday. Okay, that's the special election for our Senate seat. Please vote next Tuesday. All right, we're on page 790. This is Chapter 14, Differentiation in Several Variables, Section 14.6, the chain rule. Example 4, top of page 790. All right, what we have here, oh, sorry. I realized I didn't have this set up all the way. Okay. What we have, let me get my pen set up. F of xy is a function in two variables, obviously, and r theta are your polar coordinates, okay? The A part of example 4 says express partial of f with respect to theta, okay? In terms of partial of f with respect to x and partial of f with respect to y. Okay, now basically what's implied here, x is a function of r and theta, and y is a function of r and theta. Okay, that's probably not super notation, but you know what they are. Okay, x is equal to r cosine theta, and y is equal to r sine theta. If you think about it, think about a point in the xy plane. Here's x, y, okay? If you draw a vector to that point, okay, this is your r, square root of x squared plus y squared, and here is your theta, okay? Well, with that, this is your theta. Well, your x-coordinate here is r times the cosine of theta, and your y-coordinate here is r times the sine of theta. So that's where those come from. So it says here, express the partial of f with respect to theta in terms of partial of f with respect to x and partial of f with respect to y. Well, if r is x of r theta, f is x of r theta, y of r theta, then partial of f with respect to theta would be the partial of f with respect to x times the partial of x with respect to theta, plus the partial of f with respect to y times the partial of y with respect to theta. But we know what those are. The partial of x with respect to theta would be minus r sine theta, right? And the partial of y with respect to theta would be cosine, r times the cosine of theta, okay? Because you treat r as a constant and take the derivative with respect to theta. So let's plug these in. Partial of f with respect to theta would be partial of f with respect to x times minus r sine theta plus the partial of f with respect to y times r cosine theta. There it is. I think that's all they want. Another little observation here. What is r sine theta? That is exactly y. So this is minus the partial of f with respect to x, or minus y times that. And what's r cosine theta? That is exactly x, plus x partial of f with respect to y. Okay, so there is your partial of f with respect to theta in terms of partial of f with respect to y and partial of f with respect to x. They reverse the order of those, but it's perfectly okay. All right, now there's the A part of that. Let's look at the B part. Evaluate that partial of f with respect to theta at xy equal 1, 1, and for xy equal x squared, f of xy, xy equal 1, 1, and f of xy is x squared y. So what I think I'll do, since I don't need this anymore, that's just an illustration up here, let's erase this. Sorry, I've got to sneeze. Sorry if I didn't warn you in time. That may have been scary. Sorry about that. Okay, so what we have here, the B part, this was the A part, and that was the answer. Sorry. Here's the B part. The B part says evaluate that partial of f with respect to theta. Okay? Partial of f with respect to theta. Man, I might have to go again. At xy is equal to 1, 1. Okay? For f of xy is equal to x squared y. F of xy equal x squared y. Sorry. Okay? We basically plug in exactly what we've got down here. Partial of f with respect to theta is equal to, and I'm going to rearrange it and do it the way they did, your x, well your x here is 1, times the partial of f with respect to y. Well, let's calculate that. Partial of f with respect to y is x squared. And the partial of f with respect to x is 2xy. Okay? So plugging in down here, x is 1, partial of f with respect to y is x squared, which is 1 squared, so that's 1. Okay? Minus y is 1. Okay? Partial of f with respect to x is 2. So minus 2 times, minus 1 times 2 times 1 times 1, which is minus 2, so this is minus 1. That's it. Okay. I'm sorry, all that sneezing is really loose in my head. I'm going to have to take a quick pause here and run down and clear my head. Otherwise, I'm not going to be able to breathe the rest of the class. So hold on just a minute. All right, sorry about that. All that sneezing I did just really loosened everything in my head, and I wound up having to go clear out a bunch. So I think we got yes. Victor is here. All right. All right, now I made a bunch of announcements at the very first of the class. So if you want to hear them all, go back and listen to the YouTube video. I'll try to hit the high points for you right now. First, have you done student course evaluations? Now, please do those. The dean is on us really big time that we're supposed to get our percentages way up from what they've been, okay? So please do your student course evaluations. You know how to do those? Not on Blackboard, I don't think. They may be, I don't know, but the student course evaluations are, there's two ways to access them I know of. You might be able to get them through Blackboard, I don't know. But here's the two ways I do know about. Several weeks ago, the dean or somebody sent an email to all students. I may or may not have seen that email because I don't know if it went just to students or it went to us too. And it had on a link for how you can access the surveys. So that's the easy way. If you find that email, go to it, click on the link, and you're there. Okay? Now, if you can't find the email, or you don't know how to get to your email, or something like that, you might be able to get through it Blackboard, but I know you can get through it this way. Go to the Lawson State web page. You know what I'm talking about. And when you get there, you know how there's a series of blue tabs at the top of the page? Yes, sir. And then over near the right-hand side, there's one big gold tab that says Quick Links. If you click on that Quick Links, then you'll get a whole huge menu over here, and you'll have to scroll down, and it's not in any particularly easy to follow order, but look for surveys. I believe that's what it's listed under, or anything that it could be. I believe it's under surveys, and when you get to that, click on that, and you might have to do a few clicks, but ultimately you'll get there as well. Easiest to find the email and click that way, but if not, go through the web page to get there. Now, maybe there is a way to get it through Blackboard too. I don't know if there is, but I know the other two ways will work. Okay? So please do the student course evaluation. Please do those. Now, this has nothing to do with school. You know what next Tuesday is? Election Day. That special election for the Senate seat. Are you registered to vote? Yes, well, please vote. Now, for instance, my Tuesdays, I'm here till 8 o'clock in the evening. There's no way I'm going to be able to vote on my way home. It'll be closed before I even leave campus. So I'm going to vote before I come to work on Tuesday. I've got a final at 8 o'clock in the morning, so I'm going to try to be at the polling station when it opens at 7. Hopefully before it opens, and I'll be fairly early in line. But if there's a huge line, I may be a little late, but I've already told my class I'm voting, so just hang on, I'll get there. I think I'll get there in plenty of time. Usually, especially this late in December, probably won't be people there super early to vote. So hopefully I'll get in and out pretty quickly. So please vote next Tuesday. All right. That's nothing to do with math. Do the student course evaluations. All right. Now, you're in two of my classes, right? A paper's due in each of those, right? Research paper. Got two of those due. First test. Don't think I have that yet in either class. And second test. I don't have that in the differential equations class. I'll just be giving you your second test today in this class. Okay? That's a lot to make up in a fairly short time. Okay? In fact, I'm trying to think. In differential equations, you got a first test and the second test. Okay? Yeah, and in this class, just the first test. And you got papers in both. So please, it's a lot to do before you go to sleep. Okay? So please get those done. All right, let's see what else. Okay, I guess the rest is just what my schedule is going to be the rest of the term. This week is a normal class week. It's the last week of class. Today's the last day of class, okay? Now, technically, your papers are due today. If I don't get them today, you'll start losing points. Now, not going to be a lot of points, but you will start losing points, after today. So get them in as soon as you can, okay? Now, Today, my office hours after differential equations from 3:15 to 5:15. Okay? Tomorrow, the last day that I have classes, I have office hours from 1:15 to 3:15. Okay? Friday, I'm on the Birmingham campus, 7:45 to 11:45. Okay? So I'll be there then. So if you need to turn in something or whatever, I'll be there then. Now, next week is a weird week because it's finals week. My schedule is not the same as it's been all term. Office hours are different. Everything's different. So let me quickly go through what it'll be next week. On Monday morning, 8 o'clock, when I normally have a class, I'm running a review session for that class. It's going to go from 8 until 9:50. Okay? Not 9:15, 9:50. Okay? Anytime after that 9:50, any member of that class can come and take their final exam, which means for the rest of the week, I may be giving a final anytime during the day. Okay? So keep that in mind. Anytime after 10 o'clock on Monday, I could be giving a final. Now, I have some regularly scheduled finals, but I could be giving others anytime. So, after 10 o'clock on Monday, the odds are I'm going to be in my office. That's 265. You know where it is, right? Now, if I am giving a makeup test, I'll go to the closest classroom to my office that's not being used. So that may be in 263, 256, 261, 259, 254, any of those classrooms, or even next door at 257, okay? Or in here. So if you're looking for me and I'm not in the office when I'm not giving the final, come to all the classrooms between my office and here. Looking for me, you'll probably find me. Now, if you don't find me, it may be I had to go to an office somewhere or in the restroom or at lunch or something like that. So just hang on. I'll be back pretty quickly. So there's Monday. Tuesday morning, 8 o'clock, I have an exam in this room. Okay? So Tuesday morning, 8 to 9:50, not 9:15, 9:50, I'll be giving an exam here. And that'll probably go pretty much the full 2 hours. Okay? If students need a little extra time, I'll give them extra time, especially since I may be a little late getting here because I'll be voting that morning. Well, hopefully I'll be here in time. So anyway, I'll be here then. After 10 o'clock and until 3 o'clock, I should be in my office or any classroom in between my office and here. Okay? 3:15, I have a second mini-term class. We have our last day of class then. Mini-term classes have 1 day of class and finals and then finals. So I will be in class at 3:15 on Tuesday afternoon. Now, the odds are I'm not going to be in class the full 4.5 hours because it's a mini-term class with lab. The odds are we'll probably finish class within 2 hours and they'll probably finish their lab within an hour or two. So I'll probably be back in my office sometime later in the afternoon, but I'll be on campus until 8 o'clock that night. Okay? So first look for me here. If you don't see me here, check my office. If I'm not there, check all the classrooms in between. That's Tuesday. Wednesday, I have no finals scheduled, but that doesn't mean I won't be given a makeup test in some room between my office and here. So first check my office, 265, and then check all the classrooms as you come down the hall until you get here. I'll be probably in one of those rooms. If not, I may be in the restroom or at lunch or somewhere turning in grades or something like that. I'll be back really soon. Okay? That's Wednesday. Thursday, have nothing scheduled from 8 o'clock in the morning until 3:15. Now, at 3:15 is when I'm scheduled to give the final exam in that physical science class. However, I've given those students the option of taking it early if they choose. Here's why. A lot of those students are automotive students. Some of them are coming from out of state. Some of them are from anywhere within the state. So they're coming from all over. And basically, if I gave the exam at 3:15 on Thursday afternoon, they'd be sitting around Monday, Tuesday, and Wednesday waiting for one exam on Thursday afternoon. So I'm giving them the option. We're going to have class on Tuesday, I'm giving them the option anytime after that class is over with, if they choose to take their last test and their final, they could do so. Okay? So that's why another reason could be given a final in any room, anytime during the week. So at 3:15, I may be up here in the classroom giving a final, or I may be in the office or any room in between. All right. And then after 4 o'clock, the final should be through by then, so I'll be mostly in my office. Okay? But if some student comes in to do a late test, anywhere between my office and here. And then Friday, a finals week, back on the Birmingham campus, 7:45 to 11:45. Okay, grades are due the following Monday, I think, at 12 noon. Last term, it seems like they gave us an extra day because something in the system screwed up. So it's either going to be Monday at noon or Tuesday at noon. Whichever it is, I've got to have grades in by that time. Now, you've been here long enough. Do you realize that Student Suite gets shut down during finals week? Okay. It usually does because this old system that we use, we only have, I think it's 16 or maybe up to 32 portals now, and that's all. So if 16 or 32 students are trying to check your grades during finals week, that means there's no place that we can get on the system to put the grades in during finals week. First term they had this, it was a nightmare. None of us could get on to put our grades in. So what they started doing after that was shutting students out of Student Suite during finals week so we can get the grades in, and once we got the grades in, then they open it back up. So sometime after that, Monday noon or Tuesday noon of the week after finals, they'll open Student Suite back up. But all during finals week and until the grades are due, Student Suite will be shut down. Okay? All right. Can't think of anything else. Any questions? Okay. All right. Well, I just finished doing example 4 at the top of page 790. This is in chapter 14, differentiation in several variables, 14.6, the chain rule. And we're getting ready in the middle of that page, 790, is implicit differentiation. Okay? And what we have with this is, well, let's see. Yeah, I guess I'll go to this slide. What we have is a function, f of x, y, and z. And let's say that function is equal to 0. It's a function in 3 independent variables. Okay? Now, in single-variable calculus, we used implicit differentiation to compute dy dx, when y is defined implicitly as a function of x through an equation, such as f of x, y is equal to 0. This method also works for functions of several variables, except now you have partial derivatives. Okay? So if you had a function like this, and that you assume that z can be expressed somehow as a function of x and y. Okay? You may not be able to solve that function explicitly for z of x, y, but you can treat that as f of x, y, z as a composite function with x and y as the independent variables and z as the intermediate variable. So if you do that, what you do is partial of f with respect to x times, and they do this strangely. They say partial of x with respect to x. That's dx dx, that's 1, okay? Plus the partial of f with respect to y, partial of y with respect to x, okay? Plus the partial of f with respect to z times the partial of z with respect to x, okay? Okay, and set that all equal to 0, okay? You're taking the partial of the first with respect to x, and you go from there. Well, of course, this is 1, okay? So partial of y with respect to x is 0. Now, why is that true? That's true because we said that x and y are independent of each other. So the partial of y with respect to x is 0. There is no dependence of y on x. They're independent of each other. So that makes that middle one 0. And then we have a partial of z with respect to x because we see z as a function of x and y. So what do we have now? This is your f sub x, written in subscript notation. This term is 0 plus f sub z times dz, or partial of z, with respect to x is equal to 0. Okay? Now, what you can do from here is subtract f sub x from both sides, and then that gives you f sub z times a partial of z with respect to x is equal to minus f sub x. Divide both sides by f sub z. Okay. Divide by sides by f sub z. I put f sub x. Okay. These go out, and then you have partial of z with respect to x is equal to minus f sub x over f sub z. Okay? A little bit, I don't know if you find that surprising, but that's what you get. Partial of f with z with respect to x is minus f sub x over f sub z. Then if you went back and did the same thing for partial with respect to y, you would get a very similar result there, and that would be this one. So let me go on and just blow those up. This is what your final answer is. Partial of f with z with respect to x by implicit differentiation is partial of minus the partial of x with respect to partial of x over the partial of z. Partial of f with respect to z. Partial of z with respect to y is minus the partial of y with partial of f with respect to y divided by the partial of f with respect to z. So these two variables here, they get flipped in a minus sign. All right, there is an example with that one, and let's see if we can do that. I think it's this figure right here. All right. Calculate the partial of z with respect to x and the partial of z with respect to y at some point P111, there it is, okay, where f of x, y, z is x squared plus y squared minus 2z squared plus 12x plus or minus 8z minus 4 equal to 0. Okay. So here's your function of x, y, and z. Yep, exactly the same one. Okay. That, from earlier in the term, you see is a elliptic hyperboloid of one sheet. Okay, remember that? Elliptic hyperboloid of one sheet. Okay? That's a function of x, y, and z equal to 0. Okay. Now, we're wanting to find the partial of z with respect to x and then the partial of z with respect to y. Okay? At that point, 1, 1, 1. Okay? I think they're fairly good here. Become 1 unit out on x, 1 unit over on y, and then 1 unit up on Z. So it looks like they're reasonably well spaced there. Now the first thing I want to do is make sure the 0.111 is indeed on that curve. So let's plug it in and see. This would be 1, plus 1 is 2, minus 2 is 0, plus 12 is 12, minus 8 is 4, minus 4 is 0. Sure enough, that works. That works perfectly. Okay, that point is on the curve, and we want the partial of z with respect to x, and then the partial of z with respect to y. From what we just did, remember that now we're going to have to shrink down again. The partial of z with respect to x, if you remember, was minus f sub x over f sub z. Remember that? So the first thing we've got to do, and this, by the way, is your f of x, y, z. So the first thing we've got to do is do the partial of f with respect to x. And what would that be? There's your function right down there. What's the partial of that with respect to x? Okay. If I blow this up, then I can't write it. This is x squared plus y squared minus 2z squared plus 12x minus 8z minus 4 equals 0. And by the way, we didn't do any back in chapter 12 like this, but really what happens here, this x squared plus 12x means you have a horizontal shift. If you completed the square with those, you would see that x I think it's x plus 6, squared. So in other words, you have a horizontal shift here, 6 units. So there is your, and 6 units back that way, by the way, also. The center of this thing is back here, okay? The y is along the y-axis, so there's no shift there. The z is up 1, I think, from there, and then you're going, or maybe down 1, yeah. But anyway, that's why it's off-center, because you have these terms here and there that we didn't deal with. Sorry, back in chapter 12. So anyway, what's the partial of f with respect to x? (2x), okay. This one has no x dependence, so that's counted as a constant, 0. This has no x dependence, so you count it as a constant, 0. This does have x dependence, that would be plus 12. That has no x dependence, that's a constant, yeah. So there's your partial of f with respect to x. What's your partial of f with respect to z? Okay, that has no z component in it. This one has no z component. That next one is that's minus 2z cubed. I mean z squared. Minus 4x. You're absolutely right. And then, I'm sorry, z. Goodness gracious. I was fighting with the system. I don't know if you could tell, some box kept coming up and getting in the way. I don't know if it showed up there, but it shows up here. That's minus 4z, and this will be minus 8. Okay? So there's the partial of f with respect to x and the partial of f with respect to z. So we plug that in here, and you'd have minus 2 times x plus 6 okay, and f sub z sorry, before you got here, if you listen to the YouTube, you'll hear I just went into a sneezing fit. I don't know why. And then my head got all clogged up, and I had to break and go down and clear it out. It's clogging up again, though I haven't sneezed, but it's clogging up like crazy. Okay, that was your f sub x. I factored out a 2. Your f sub z, I'm going to factor out a minus 4 in the denominator. Well, the minus will wipe that out, and that will give you 4 times z minus or plus 2. Yeah, because I factored out a minus 4. Okay, these go out. That leaves you a 2 here. So what we have here, partial of z with respect to x minus partial of alpha with respect to x, partial of alpha with respect to z. Goodness gracious. All right. Just for some reason, my skin is crawling. I don't know if it has to do with sneezing or what. So this comes up being 1/2 x plus 6 over z plus 2. Okay. That's the partial of z with respect to x. Okay. Now we want that at P111. Okay. So in other words, let's plug in at P of 1, 1, 1. So this will be 1/2 of 1 plus 6 is 7, and 1 plus 2 is 3, and that would be 7/6. Got it. Okay. Sorry, I'm about to sneeze again, I'm afraid. Now let's do the partial of z with respect to y. Well, from what we did before, what would that be? Minus f sub, no, you flip them over, y over f sub z. Okay? And that would be equal to, we haven't done partial of f with respect to y. Partial of f with respect to y would be, let me erase these things that are hiding what I need to see. Okay. All right. Sorry, my head's clogging up again. Partial of f with respect to y. Okay? The only term in here with a y is that one. And what's that partial with respect to y? Two y. Okay? So let's plug in just like we did before. Minus 2y divided by your f sub z was the same as it was before. It's a minus and minus, so let's make that a plus. And we factor it out of 4 times z plus 2. Okay. Now let's calculate that at the point 1, 1, 1. Okay. 2 will go into 4 twice, and you get y is equal to I'm sorry, I was plugging in 111. Goodness gracious. I had it so clogged I can hardly breathe. Okay, y is 1. Here we had a 2 times z plus 2. Z is 1. 1 plus 2 is 3. So that is 1 over 6. And that's exactly what they got at the top of page 791. Sorry. I think I'm going to have to go clear my head one more time. But there was one other part to that problem. It said, what is a graphical interpretation of those partial derivatives? The partial of z with respect to x. So that's how is z changing as x is changing at the point 111. Okay? Well, z here is increasing as x is also increasing. You're coming this way. So that gave you 7 over 6. Z is going up 7 units for every 6 that x goes this way. Okay? How is z changing with respect to y? Well, over here, z is still increasing, well, y is increasing, but not nearly at as rapid a rate because you're twisted around on this. Here, you're almost lined up with the maximum curvature here. Here, you're over here where you're not got as much, still increasing with an increase in y. Z's going up 1 for every 6 in y. So it's not going up nearly as fast. Okay? Don't know if that's what they meant by graphical interpretation of those derivatives. Okay. They really don't say a lot, but it's there. All right, one more figure here, and that's this one. All right. Implicit differentiation is based on the assumption that we can solve the equation f of xyz is equal to 0 for z in the form of z as some function of x and y. Otherwise, those partial derivatives would have no meaning. Well, here with a cylinder like this, a right circular cylinder going infinitely up or down, here is the equation for it. X squared plus y squared minus 1 is equal to 0. There you've written it as f of xy is equal to 0. Okay? Well, there is no z in here. Okay? So there is no partial of f with respect to, partial of z with respect to x. Because z is vertical there. If you can't change x in it, well, it's because x on the cylinder isn't going anywhere, okay? Z is going straight up or straight down at that point x. It's not got any variation because x is not changing this way or that way. Now, if you went around the cylinder, it changes a little bit, but then there's no dependence on z at all either. So this one has no partial of z with respect to x, because z doesn't change as x changes. X changes, z is completely independent of x and y. Okay? That z goes up and down without any change of x or y. So I think that's what they're talking about here. So f sub z is always 0, because there is no z dependence there, and of course you can't divide by f of z then, not defined. All right, there is a summary there at the end of 14.6. Do you want to do the preliminary questions in 14.6? Up to you. Okay, let's do this. All right, I think this is the last slide, so let's go back to this. I thought I was going to have to go clear my head, but it seems to have cleared a little on its own, so let's keep trucking if we can. Okay. This is preliminary question 1. Let f of xy equal to the function xy, x times y, where x is equal to uv and y is equal to u plus v. Okay? What are the primary derivatives of f? Okay, what are the primary derivatives of f? Okay, now that's a rather almost nebulous term here. Excuse me. And I think in the text, yeah, on the bottom of page 788, it says we keep track of the dependencies between the variables. They have a little figure there. As in that figure. As an aid to remembering the chain rule, we refer to the partial of f with respect to each of these main things here, in this case it would be x and y, as the primary derivatives. They are components of the gradient of x, okay, a gradient of f. Okay, that's basically all they say about it. So, from what their definition is, the partial of f with respect to x is a primary derivative. What would that be? If f of xy is equal to x times y, what's the partial of f with respect to x? Y, exactly. And the partial of f with respect to y is x. Okay. Now, by their definition, I think that's all they're looking for, but let's just make sure. This is 14.6, preliminary question. You know what they have? Partial of f with respect to x and partial of f with respect to y. They don't even evaluate what they are. They just say that. So yeah, we got it. Okay. Dumb. Okay. It says, what are the independent variables? These are really simple questions. We went into more detail than they need. All they were looking for is that and that. That's all they were meaning, not even what their values are. Okay? What are the independent variables here? Actually, x and y look like they would be, except that then you define x in terms of uv and y in terms of uv. So that makes x and y intermediate variables, with the independent variables being u and v. And that's all they were looking for, u and v. Okay? Again, these are really simple questions, u and v. All right? Let's go to number 2 and 3. These have, sorry, one set of instructions here. So for questions 2 and 3, suppose that f of uv is equal to ue to the v where u is rs and V is R plus S. Okay. All right. Got that set up, but I was trying to figure out where in the world the question was. Here's the question. The composite function f of uv is equal to, and here are three possibilities. A, rs e to the r plus s, rs e to the r plus s, B, re to the s, or C, rs e to the rs. Okay. It's just asking what is that composite function equal to. All right. And again, don't try to make it any more difficult than what it is. Here they told you what alpha of uv is u e to the v. So basically what you're doing is you're plugging in u what u is and v what v is. Okay? So this composite function, u is rs, and f is that u times e to the v, and v is r plus s. That's it right there. A. Do you see that? Again, it's just a plug problem. It's not anything esoteric. It's just plugging it in. So that would be A. Exactly. All right. Number 3. Let's see if we go a little deeper there. What is the value of f of uv at rs, ordered pair rs, equal 1, 1. Okay? Now, from what we just answered, f of uv is this thing right here. So what we do is plug 1, 1 in for r next. What would that be? 1 times 1 times e to the 1 plus 1. So it's e squared. You see that? This is what f of uv is, this thing right here, this A answer here. And then what's the value of that when rs is 1, 1? That would be 1 times e to the 1 plus 1. Okay, so that would just be e squared. Okay, that better be what they get in the back. Let's see. Yep, e squared. Very good. All right, number 4. According to the chain rule, this is 4, the partial of f with respect to r is equal to what? Here's the A part. Partial of f with respect to x times the partial of x with respect to r plus partial of f with respect to x times partial of x with respect to s. Or B, partial of f with respect to x, partial of x with respect to s, plus the partial of f with respect to y, partial of y with respect to r. Or C, partial of f with respect to r, times partial of r with respect to x plus the partial of f with respect to s times the partial of s with respect to r. No, x. Okay, I can't read. Okay. What do we mean by that? Okay? Partial of f with respect to r. Well, okay. Now, let's just assume here we're talking about polar coordinates. You don't have to be, but that would be r theta, not rs. Okay. So let's say we're not. Okay. Just all right. Partial of f with respect to r. Let's assume that f is a function of x and y are functions of r and s. So this would be partial of f with respect to x times partial of x with respect to r. Perfect. This next part isn't right, though. Okay? I don't think it's any of these. Plus partial of f. This should be with respect to y, like this one. But then it should be, if that was an r there, this would be the right answer. Did I copy it wrong? Yes, I did. Yes, I did. Okay. No wonder. My eyes left the page there. Okay, that's your answer. Okay, I was going to say none of those are correct. Because you take the partial of f with respect to x and then the partial of x with respect to r. Plus partial of f with respect to y. No, you don't do x again. You don't even introduce the s. S has nothing to do with this. So A is wrong. B is right now that I've corrected. Partial of f with respect to x times partial of x with respect to r plus partial of f with respect to y times partial of y with respect to r. Yes. Because you see, this looks like this cancels out partial of f with respect to r. This looks like that cancels out partial of f with respect to r. That's what we got. You don't introduce an s in, and you sure don't mix around your variables there. You don't have this being this times something else. That would make no sense whatsoever. So C is obviously wrong here. And you don't even introduce the s there. You want partial of f with respect to r, not with respect to x. That would be with respect to x. All right, that was 4. So it should be B. Let's see if it is. I didn't check it, but 4 is B. It surely is. All right, I'm going to erase all these if that's okay. Okay. Wow. Number 5. Suppose the x, y, z are functions of the independent variables u, v, and w. X, y, z functions of independent variables u, v, and w. Okay. Which of the following terms appear in the chain rule expression for partial of f with respect to w? Okay? All right? Let's just write down what partial of f with respect to w is. That would be the partial of f with respect to x times partial of x with respect to w, plus partial of f with respect to y times partial of y with respect to w, plus partial of f with respect to z times partial of z with respect to w. To me, it's easy going to write down what it is. You see, ultimately, you need to have partial of f with respect to w. Those have to be the same, those have to be the same, those have to be the same, and what you have left is the same as what you have left. That's how you do the chain rule. Okay? So, let's see what their options are. which of the following terms appears in this? Here is A, partial of f with respect to v. Stop right there. Can't happen. Partial of x with respect to v makes no sense at all. None, okay, none. Not that one. B, partial of f, that makes sense. With respect to w, no. That's an independent variable, not dependent. Partial of w with respect to x, that would be the partial of f with respect to x, not the partial of f with respect to w. So that one's not right. Better be C, okay? Partial of f with respect to z, certainly, that's possible. Partial of z with respect to w, yes, that's that one right there. That's it. Better be C. 5 is C. Good for them. And number 6, with notation as in the previous question, does partial of f with respect to v appear in the chain rule expression for partial of f with respect to u? No. Because u and v are independent variables. Why would partial of x with respect to v show up when you're looking for partial of f with respect to v? U, I'm sorry. And the answer should be no. And it is. All right, homework exercises here. Do number 1. Do any of the odds 3 through 9, any of the odds 11 through 15, any of the odds 17 through 25, any of the odds 27 through 31, any of the odds 33 to 41 through 41. Okay, and you can stop there. Oh, yuck. We are so out of time. I don't know which is more important to do. Okay? I sure hate that we haven't gotten further along than what we have. Let's do 14.7 for right now. Not going to be able to do a lot, but let's do what we can with it. Goodness, I need something to drink. I rushed through lunch and got lunch eaten, but hardly got anything to drink. So I'm dry. That may be why my head is messing up some too. My eyes hurt. Okay, I'm that dry. Okay. Now, pretty picture here, huh? When we were in single variable calculus, when we're optimizing something, we're looking for max and min, right? Well, in multivariable calculus, we kind of do the same thing, except now we have partial derivatives. By the way, maximum or minimum is where the first derivative in single variable calculus, where the derivative was 0, or sometimes maybe not defined, or something like that. Okay? In multivariable calculus, like we have here, your function f of xy, that's your z value here, is a function of x and y, and you see you have a local maximum here, you have a local minimum down here, and then you have a global maximum up there. This happens to be a global minimum down here. That's just a local maximum here. All right, Betty is here. Well, we got 2 out of 3 today, so far. We're missing Jasmine, who's generally pretty much here, okay? Now, what do we mean by that? Okay? Well, it's kind of the same thing as what we did before in two-dimensional calculus. When you had a line here, your x-axis, say, here, and your y is equal to f of x up here, as a local maximum if, for some interval around some value of x equal a, say, there, for some interval there, the f of a was always greater than or equal to your other f of x in that interval. Okay? Well, now we have a disk around the point R. Let's see. Okay. The point P. And that disk has a radius of R. That's what the R stands for. P is this point here, x, y value here. Okay? Here is x, there and y. And then some radius around that. And that disk is centered there with some fixed radius there. If for every value that's in here, x, y value that's inside that disk, if all these values are less than or equal to the value at that point P, then that point P is a local maximum. That's a local maximum. This is a local minimum. Because all the values around here are greater than or equal to that. All the values here are less than or equal to that. All the values around here are less than or equal to that. Okay? So that's what we mean in two-dimensional and in multivariable calculus, what that means. Okay? So that means you're going to have partial derivatives, both with respect to x and with respect to y. Z is your dependent variable, x and y are independent. Okay. That leads to this definition for your, goodness, my eyes are aching. Right? Your local extreme values, a function f of x, y, has a local extremum, that could be a maximum or a minimum, at this P of AB, A on x, B on y, if there exists an open disk D at that point P and R around that point P within some radius of that point P, such that f of xy for every xy inside that radius, okay, is always less than or equal to f of AB, then f of AB is a local maximum. That's for all the xy's that are in that domain, the PR, the domain or the disk, open disk, at point P of radius R. So local minimum if every f of xy that's around that point AB that's greater than or equal f of AB for all the xy's that are in that disk around point P of radius R. Okay? Pretty much, I hope, what we were expecting to see. All right? Now, I think they have a, no they don't. Yuck. For some reason, they don't have the next figure here. So we're just going to have to go straight to critical points without the figure in mind. If you got your book, you can see these, I think. Okay. So we mentioned local max, local min. A critical point, a point P at AB, in the domain of f of xy is called a critical point if these conditions hold. That's two variable problems, f of xy. If the partial of f with respect to x at AB is 0, or that partial doesn't exist. Remember, we had the same thing when we were doing single variable calculus. Not only would it be a critical point if it was 0, but it also would be a critical point possibly if the first derivative didn't exist. And, not just or, but and, the partial of f with respect to y at AB is either 0 or doesn't exist. So we now have two conditions. So if f of xy was 0, f sub x at AB was 0, okay, its derivative, partial derivative is 0. But partial of f with respect to y was not 0, then that would be a critical point, okay? But if f sub x of ay was 0 and f sub y was, or f of sub x of ab was 0 and f sub y did not exist, that would still be. Or if f sub x of ab does not exist and f sub y ab was either 0 or doesn't exist, then those would be critical points. So you have to have an and, both fitting, but of the both, you have an either or. Okay. So it's a little more to take into play there. That then takes us to Theorem 1, which is Fermat's theorem. Okay? Now, Fermat was an interesting character. If my memory's right, and some of these, especially the French ones, I get sort of crossed up, but I'm almost certain Fermat was not technically a mathematician. He was kind of a philosopher. I think he studied theology, but he loved to play around with math. So he was a really good mathematician, but that wasn't his training. That wasn't his profession. But he loved doing it, and he was good friends with a bunch of people who were very good mathematicians, so he would interact with them and say, well, how about this, you know? And he came up with a lot of very insightful. Here's one of his theorems. If f of xy has a local minimum or maximum at that point P at AB, then AB is a critical point of f of xy. Okay? Now notice what it doesn't say. It doesn't say if P is a critical point, then it's a local maximum or minimum. It may not be. But if it is a local maximum or minimum, it's got to be a critical point. Okay? AB has to be a critical point. So that was one of Fermat's theorems. And sure enough, that came out true. You can see and do the proof if you would like. Okay? All right. Now, I'm going to rush this through. Okay, this is example 1. All right. Show that f of xy, which is 11x squared minus 2xy plus 2y squared plus 3y, has one critical point, and then it says use this figure to determine whether it corresponds to a local maximum or minimum. I think that's going to be pretty easy to figure out, that second part. But it says let's show that it has one critical point. So what do we better do to show that it has a critical point? Take the partials. You're absolutely right. So let's go back. I thought I was going to have to do it. So, oh, goodness gracious. Where did that come from? Partial of f with respect to x would be what? There's 22x minus 2y. Exactly. Done. Stop. Partial of f with respect to y would be
minus 2x plus 4y plus 3.
Okay. Now, to have a critical point, okay, this has to either be 0 or not exist. Well, guess what? That's not going to not exist anywhere. These are all polynomials. They exist everywhere. So not exist is not an issue here. It's whether they're equal to 0. Okay? Well, what can we say about that? This is where 2y is equal to 22x, which is saying where y is equal to 11x. Right? Down here, this is equal to 0 where? Well, let's see. Let's do sort of the same thing. Okay? this will be where 4y is equal to 2x minus 3, right? Okay? So let's plug that y in there. That would be 44x equal 2x minus 3. This will be 42x equal negative 3. So x equal, this doesn't look right at all, minus 1 over 14. What? Yep, that's it exactly. This figure is really a bizarre figure. I don't feel like that. So x equals that, then you plug in up here, y is equal to minus 11 over 14. And sure enough, there is your critical point. Minus 1 over 14, minus 11 over 14. That is your critical point. And that's exactly what they found here. Okay? So, I think with that one, sadly enough, we have to stop. Okay? Now, I can't remember. Did I pass out to you your test last time? Okay, I didn't give one to you because you weren't here. Okay, because I saw that I had made copies, but I said I didn't do so. And I said today, okay, I think I'll pause this.